now that we have seen an intuition about how things roughly should work, let's try to be a bit more precise and go into solving linear ODE systems. So if we are looking at x prime equal ax, when we are in one dimension, we have x prime equal to ax, where a is just one real value, and we know that the solution is x as a function of time is a constant that depends on the starting point and exponential of at. And we find that this is a good approach. So we try to find something similar for our solution for our vector problem. We guess, we try, x vector equal a vector xi times the exponential of rt, trying to mimic the situation we have in one dimension, where we want the exponential, the exponent r to be real and xi to be also real. We'll see that that is actually not always the case, but we'll start by assuming that everything we're dealing with is real. So if we do this, then x prime, well, luckily this is an easy situation for the function x, is just a constant vector times a function of time. So the only part we have to derivate with respect of time is the exponential, and the exponential is easy to derivate. So x prime is equal to r times xi times exponential of rt. So if we take this and plug it into our ODE system, we have r xi e at the rt equals to a xi e to rt. And we can cancel out e to the rt. Think about why we don't want to cancel out xi. Well, xi is a vector, and on one side is multiplied by a matrix. That means that the matrix is going to mumble up all the component of xi, while exponential of rt is just a scalar value. So we can shift that around and divide by a scalar value at any point. So now we have r xi equal a capital A xi. Does this remind us of anything? Well, A is a square matrix, and xi is going through the transformation of a square matrix and returning itself multiplied by a scalar. This means that that scalar is an eigenvalue, and xi itself is an eigenvector. So for any eigenpair r xi, xi exponential of rt is a solution to our ODE system. For example, if we take this x prime equals 3, 2, 1, 2 times x, we have a matrix 3, 2, 1, 2, and we can compute the eigenvalues of it. That means we have to compute the determinant of A minus lambda I, where I is the identity matrix. That gives us the determinant of 3 minus lambda, 2, 1, 2 minus lambda. And if we compute the determinant of this thing is 3 minus lambda times 2 minus lambda minus 2. And if we do the steps, we find that the eigenvalues of this matrix are 4 and 1. Then we want to compute the associated eigenvector. So we take one of the two eigenvalues, 4, and compute the associated eigenvector. That means that the associated eigenvector solves 3 minus 4, so A minus 4i times xi equal to 0. And we can do the computations. And we notice that A minus 4i simplifies to minus 1, 2, 1 minus 2 times xi. And you might immediately notice how the first line is the second line multiplied by minus 1. And we want this singular matrix, singular because two lines are dependent, linearly dependent on each other, multiplied by xi is equal to 0. We can solve this and find that xi1, the eigenvector associated with the eigenvalue 4, is the vector 1, 1/2, or any multiple of this. But 1, 1/2 is pretty nice to work with, so we're going to keep that. We can also compute the other eigenvector associated to the other eigenvalue 1. Then if we compute that, we get the vector 1 minus 1. Then we have, as first solution, the first eigenvector multiplied by the exponential of the first eigenvalue times the time, that is the vector 1/1/2 multiplied by the exponential of 4t. And the second solution that we find is the eigenvector 1 minus 1 multiplied by the exponential of time. Those are the two blocks we're interested in. So if we're looking at x prime equal to ax, if A, that is a square matrix of real values n times n, if A has n eigenpairs, R1 xi1, R2 xi2 down to Rn xin, with xi1, xi2 down to xin linearly independent, then the general solution is given by the linear combination of the solutions associated to each of these eigenpairs. So in particular, it would be x equal c1 times the first eigenvector, xi1, times the exponential of the first eigenvalue times time, r1 times t, plus c2, xi2, exponential of r2, plus all the terms you have just computed in the eigenpairs, plus cn, xin, exponential of rnt. The important bit here is that you need the eigenvectors to be linearly independent. If they might be, it's unlikely, but they might be linearly dependent. They're always linearly independent if the eigenvalues are different, but they might be linearly dependent if the eigenvalues are the same. This case we're going to see next week.